Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. So in this video lecture, we will see the basic concepts of operational amplifiers, specifically known as OPAMP. The topic has been taken from Unit 3 and for the subject as defined in the AKTU syllabus, that is Fundamentals of Electronics Engineering in Unit 3. Let's start. So this complex video lecture has been made only to give you the concept for applying the numerical problems, to apply all the concepts for the numerical problems. And you will see I will tell only one technique to solve any kind of OPAMP numerical. So after this video lecture, you will be able to solve any problem for the OPAMP as far as your syllabus is concerned, and no question above that level can come, and you will be solved the toughest question from the OPAMP if you adopt this particular concept based on KCL and KVL only. So here, first of all, we should understand why we are preferring the operational amplifiers, because it gives a very high gain, and then it has a very high infinite input impedance. It has very low output impedance, approximately equal to 0, and infinite common mode rejection ratio, infinite slew rate, that is change in output voltage with respect to the time. Now, these are some qualities of the OPAMP, as you can see, and so that we can use it very frequently in our electronic devices or electronic circuit. And of course, the OPAMP has really made up of differential amplifier as the second stage of the amplifier. There are 4 basic stages of the amplifiers: input stage, intermediate state, that is differential amplifier, and after that your level shifting stage, and then output. So these are the some theory portion from the OPAMP, but basically here in this video lecture we are going to discuss the numerical concepts only, so we will talk about that only. So here considering there are 2 inputs for any operational amplifier and 1 output. 2 inputs. First input is input 1. This is positive. Positive means there will be no inversion of the given input. That means there will be no phase shift of the given input at the output. This is inverting input. There will be a 180-degree phase shift. The waveform will invert. It will be amplified, of course, because we are using OPAMP as our amplifier. It will be amplified, but it will be inverted also. From pin number 6 of the OPAMP, we take the output, as you all know. So here this is the equivalent circuit for the OPAMP, the differential input V1 and V2. The pin number 2 is the inverting input, and pin number 3 of the OPAMP IC is the non-inverting input. This is showing the infinite impedance, input impedance of the OPAMP. Yes. Pin number 6, at pin number 6 from the OPAMP IC we are taking the output, and this Z out is 0. The output impedance is very low for the ideal OPAMP, and that is 0, right? The gain of the OPAMP will be V out upon V in. V in is of course V2 minus V1. Okay. So this is the equivalent circuit of the OPAMP. Very important point. Now we are going to start the numerical concepts, and for which the identification of closed loop and open loop is very important. So we should identify whether your OPAMP is amplifying in closed loop configuration or your OPAMP is amplifying in open loop configuration, right? First of all, you need to find out. Then accordingly, you will apply the rules for closed loop configuration and open loop configuration, right? If the OPAMP is in open loop configuration, that means it is having no connection between input and output, that is no feedback at all, and the gain can exceed from 10,000 or more. In the closed loop configuration, the gain can be reduced, but the feedback has always been given at the inverting input. Always remember. You should be very, very careful for closed loop configuration, and you have to check where the feedback resistance has been connected from output number 6 to input number 2, that there should be a connection between point number 2 and point number 6 of the OPAMP IC, right? Which is known as negative feedback. This is output terminal, this is input terminals, and this is inverting terminal, this is non-inverting terminal, right? And we have connected this feedback resistance RF between the terminals 2 and 6. This is important to find out the configuration of the OPAMP, whether it is working in open loop or whether it is working in closed loop. This is very, very important, right? Next. Now coming to the numerical concept for the OPAMP. Numerical concepts of the OPAMP, right? First point that I told is check the configuration, whether RF is connected to the input or not. So first of all, you need to check the output, check the configuration. This is feedback configuration or closed loop configuration, right? Next, if there is no connection between input and output, this is open loop. There is no resistance, no capacitance, nothing between point number 2 and point number 6. So this is open loop, and this is closed. After identifying the open loop configuration and the closed loop configuration, we will see from which terminal we are giving the input. Output terminal is fixed, that is point number 6. But we will identify from which terminal we are giving the input, right? So the terminal for input, see here, the terminal for input is VO. If I am giving input to my this terminal, let's say, whether it is AC or it is DC, if I am giving this input, then the OPAMP is working in inverting mode, Okay, right? This is very important. If I am giving input to my this terminal, the OPAMP is working in non-inverting configuration. If input has been given at the non-inverting terminal, OPAMP is in non-inverting configuration, and if input has been given at the inverting terminal, the OPAMP is in inverting configuration. So you need to identify whether your OPAMP is in inverting configuration or non-inverting configuration. It should be very, very clear first of all. After confirming the inverting and non-inverting mode, there is one point also, which is you may get the questions where some voltage has been applied, at the inverting terminal 2 and non-inverting terminal 2 along with the, maybe feedback resistance, or maybe feedback resistance not present. Okay, so here the difference voltage will be taken. So we have applied some sort of differential input to the OPAMP, and we can't say whether it is in non-inverting or inverting configuration. It will totally depend on the values of V2 and V1. So this is the this is the prime important point you need to identify. First of all, you need to check for the closed loop and open loop. Secondly, you will check whether it is OPAMP is working in inverting configuration or non-inverting configuration. Yes, and then let us start with the numerical. Okay. Here a very, very important point comes, that is virtual ground concept. What's that? This is the base for your OPAMP numerical. Virtual ground concept. What's that? This is basically we are applying for ideal OPAMP here only. We will apply the virtual ground concept for ideal OPAMP, and which states that this point A, this point B, the voltage of this point A is always equal to the voltage of this point B. VA is equal to VB. Okay, VA is equal to VB at each and every condition for any ideal OPAMP. If I make these two voltage points to be equal, then we can apply our concept to the numeric, right? Let us start with taking any example for the OPAMP circuit, and always remember this VA and VB will be applied, right? Let us start with any numerical. Here I am making the OPAMP circuit. This is the minus terminal, the inverting terminal, and this is the non-inverting terminal. From pin number 6 we are taking the output. From here we have given some, this 2 kilo ohm resistance, and this point has been grounded, and this is some 1.5 kilo ohm resistance, and some DC voltage we have applied of 6 volt, let's say. Now we need to calculate the output voltage. Okay. So we should be very clear how we should proceed for the OPAMP numericals, right? We will solve it now. This OPAMP is in closed loop. Identify first. This OPAMP is in closed loop. Second, the input has been given in at the negative terminal. It is inverting. Just keep it in your mind that the inverting mode is on closed loop configuration, right? Now we will apply third the VG concept, that is virtual ground. The virtual ground concept. These three you need to apply. Now we will apply the virtual ground concept, which states this point potential is 0 volts. V is equal to 0 at this point. Then this point potential is also at 0 volts from virtual ground concept, right? I repeat, virtual ground concept give you the points, 2 points A and B, inverting and non-inverting terminals. The point voltage potentials are equal, and the voltage at the inverting and non-inverting terminals are always equal according to the virtual ground concept. So here, if this point is at 0 potential value, then this point will also be at 0 potential value. Now applying the KCL at the virtual ground concept, okay, at this particular point we will apply the KCL. Okay, so since the DC battery has been applied, some current will come out from the supply. This will pass through the resistance. According to the KVL, this will be the positive terminal of the resistance and this will be the negative terminal of the resistance. Since the ideal OPAMP has infinite input impedance, so 0 ampere current will go into the OPAMP. No current is going into the OPAMP and all the current will go from the feedback resistance. No current is going inside the OPAMP because OPAMP is offering infinite input impedance. Okay, infinite input impedance has been offered by the OPAMP. So no current is going inside it, and applying the KCL at this particular point, that is 6 minus 0 upon 1.5 kilo ohm is equal to, this current is equal to this current, 0 minus VO upon 2 kilo ohm. The current here is equal to the current here. The current here is equal to the current in the feedback resistance. That what I did is 10 raised to the power 3, 10 raised to the power 3 cancel. 6 upon 1.5 is equal to minus VO upon 2. VO giving me the value of 6, 3, So our problem has been solved, and this is VO is equal to minus 8 volt we have obtained by applying simple VG concept and the simple KCL, and this technique you can use for any OPAMP circuit and you will get the answer for sure. Next, this one is as an example for the closed loop configuration. Now I will come to the open loop configuration for the OPAMP circuit. So here this point is A, this point is VB, we have supplied VA, and this has been supplied VB. Let's say this is the input we have applied at the OPAMP. No feedback has been given, and we have the open loop configuration. See, the idea for open loop configuration is slightly different from the closed loop configuration. First of all, I told you, first of all, you need to identify the open loop configuration and the closed loop configuration. So we have clearly understood that the open loop configuration is applied for this particular given circuit. Now let's say I take some numerical value for the better understanding. So let's say VA I have applied around 6 volts at the input terminal, and some 3 volt battery has been connected at the non-inverting terminal. Then what should be the output? What should be the output for the OPAMP? The output has been asked for this thing. This is the kind of numerical. So here for open loop configuration, the OPAMP works as comparator circuit, right? It will work as comparator circuit, and it has only two possible outputs, that is plus VSAT and minus VSAT. This is the concept for open loop configuration, right? So here in this configuration, the OPAMP is going to work as comparator circuit, right? Let us cut it so that there should be no confusion at all. This is working as a comparator. OPAMP is working for comparator in open loop configuration, comparator circuit. Since this VA is greater than VB, the output of the OPAMP will be minus this output is minus V saturation voltage for the OPAMP circuit. The output of the OPAMP will be minus VSAT. There are only two possible outputs for the OPAMP. If the voltage at the inverting terminal is greater than the voltage at the non-inverting terminal, the output of the OPAMP is minus VSAT, and if the voltage at the non-inverting terminal is greater than inverting terminal voltage, then the output will be plus VSAT, of course. So there will be two outputs. Suppose we would have given this to be 5 volts and this to be 3 volts, then output would be plus VSAT. So we have learned how to solve the OPAMP numericals, right, for open loop configuration and closed loop configuration. Apply the concept of KCL. See for the configuration, make sure in which configuration your OPAMP is working, whether it is working in closed loop or it is working in open loop, number one. And then you will apply the concept of virtual ground, right? And then you will see the input voltages applied at the inverting and non-inverting terminal, whether it is inverting terminal voltage or non-inverting terminal, and always check the resistance. The resistance needs to be connected at the negative terminal for feedback. Feedback to be given, always to be given at the inverting terminal of the OPAMP, and accordingly you can apply the concept. If I want you to explain again this particular, please check. You will go only in this direction, in the direction of current. This 6 minus 0 upon the resistance, this 0 minus VO upon this resistance. This will give you the current. Nothing else I have done. You can try a lot of numericals on this concept and you will definitely get the values correctly. So here we finish this video lecture. Thank you.